Today, we are going to be looking at the material selection process of a part that is present in almost every car, either in the trunk or in the hood. We will go through the functional requirements as well as the intended application for this part that we considered for the material selection. After we reveal the selected material, we will walk you through the specific heat treatments and strengthening processes, as well as the finishings that are beneficial and required for this material. The overall aim of this process is to analyze a design in relation to its standard operating environment, as well as the potential for environmental degradation. And this study highlights a thorough material choosing process that culminates in the selection of a material that satisfies the highlighted constraints and will result in optimal functionality of the part. Under the constraints of transportation, we are going to be looking at the lift support struts that hold up the hatch of a vehicle. These are the gas support rods on either side of the trunk of a vehicle that help open the liftgate so you don't have to do it manually. Specifically, we will consider the gas cylinder that sustains the internal pressure and houses the piston rod. This is the kind of part that might not be obvious at first, but is incredibly important because it is the component that supports the weight of the hatch when it is open. In this video, we are specifically going to be focusing on the support strut of a 2010 Toyota Sienna. For some background, this vehicle for this research is currently in Waterloo, Ontario, Canada, and has been parked outdoors for most of its life, surviving 8 winters, 8 Canadian winters. Imagine all the stresses on the material throughout this time. This part is mostly made of metal, and since it is directly exposed to the weather, rain and snow when the trunk is open, as well as oxygen, it is corrosion prone, and quite visibly, some key areas seem to have undergone corrosion. In fact, if the corrosion rate is not controlled, it can spread to the rest of the strut, and this drastically reduces its time to failure. As said earlier, the function of this strut involves the mechanical load that is applied at different points on the material. The pressure in the cylinder must then be able to sustain this load. This requires that the material for the cylinder must be chosen appropriately to bear these stresses. Considering the fact that the trunk is supported by 2 of these parts, the force necessary to support the trunk has to be divided by 2, and equations of equilibrium have to be derived so that the system can remain in balance. To understand the uses of this part, let's take a closer look at the constraints and functional requirements for our design and our selection. First, we have to consider key factors such as the maximum internal pressure the cylinder must be able to contain. We first calculated the force that the strut itself must provide. From the free body diagram of the loading, we determined that this maximum internal pressure should be at least 16.12 megapascals. Also, some other functional requirements include the fact that any cracks cannot move through the part at the maximum stress. The part should not cost more than $1. The material should have very good durability in fresh and salt water because of the part's environmental conditions, rain and possible road salt exposure. And also that the bore diameter of the cylinder has to be 10 millimeters in width in order to properly accommodate the piston rod. Due to the geometry of the chassis, the measurements of the cylinder were also constrained. Specifically, the maximum thickness of the cylinder is 7.5 millimeters. Choosing the best material involves a thorough material selection process, and this involves using softwares such as the CES EduPack database and Ashby diagrams. We decided that the functional requirements that could be demonstrated by a materials performance index are the maximum stress in the material and the fracture toughness of the material. The most important objective of this whole process is to minimize the cost of the part as much as possible, and this was done by describing the cost function. Cost is equal to the volume of the cylinder multiplied by the cost per unit volume of the material. An equation to describe the maximum stress in a cylinder was found as a function of the internal pressure, bore radius, and the thickness of the cylinder. Since the thickness appears directly in the stress equation, and as a result of the volume term in the cost function, it was decided to be the free variable, which ultimately led to our first MPI. We defined this as the cost per unit volume against the yield stress of the material. In turning our constraints such as the maximum cost, we were left with 1,685 materials for selection. We next added the constraint to the maximum thickness. Using this, we were able to determine the minimum yield strength required. This continued to reduce the number of materials available, and by developing an equation for the fracture toughness in terms of the maximum thickness of cracks, as well as the previous cost function, we were able to develop a second MPI where we defined this as the cost per unit volume measured against the fracture toughness of the material squared. With the aim to minimize corrosion, we placed another limit which ensured that the durability of the material in fresh and salt water are excellent. We did this because the part is exposed to moisture and road salt during colder periods. This drastically reduced our options. At this point, we determined that the fracture toughness of the material was the more important constraint, as it determines the stress required to pose the risk of the cylinder leaking. So, we decided that to account for the crack propagation, the material with the lowest value of the second MPI would be chosen, which resulted in selecting 15 5-pH martensitic stainless steel in the H1150M condition. With previous research, it was determined that some form of heat treatment would be beneficial for the strength of the part. Considering that the continuous opening and closing of the trunk can lead to fatigue, and that the changes in weather would expose the material to different levels of oxygen and water, increasing the strength of the material will increase the time to failure and also provide us with a more durable material for the hatch. According to the CES database, the H1150M condition involves solution annealing, age hardening, and air cooling, where the material is heated to bring out precipitates that act as obstructions to dislocation movement, thereby increasing the strength of the material. With the solutionizing stage, where we heat the material to a high temperature, the material should be heated to a temperature of around 1040 degrees Celsius, plus or minus 14 degrees Celsius, for 30 minutes. As for the quenching, the material should be cooled to below 32 degrees Celsius in order to complete the martensitic phase transformation. The material should now be in a strong but brittle state. Using age hardening, the material may be made more ductile and machinable. To do this, the material should be heated to 760 degrees Celsius plus or minus 8 degrees Celsius for 4 hours and then air cooled. Generally, the age hardening process should allow further diffusion of the atoms. Getting a more ductile material comes at the expense of strength, however. Some ductility is useful in this application, as it would give an indication of failure before rupturing. Using the treatment, the specific properties of the material may be controlled, whether that is an improvement in strength or ductility. For the finishing processes, the original part was finished electrostatically with chrome, which has some advantages. It provides a clean finish, it has good durability, it improves the hardness, and is ultimately corrosion resistant. Another option would have been nickel plating, which provides an equally good finish for corrosion. But the negative side effect is that it tarnishes quicker than chrome. We could have also galvanized our part, but the quality of the finish is not the best and generally looks unpresentable compared to the chrome finish. Another great option would have been cadmium plating due to its strong corrosion resistance. However, it is not ideal for this application as it is exposed to the inside of the vehicle and is generally a toxic process. With all these in mind, the best option seems to be the chrome finish, and generally, this is giving a black coating. As an engineer, the control of properties of materials is vital for proper material selection. The extensive processes involved in choosing the optimal material, determined through derivation of MPIs in relation to the functional requirements of a part, resulted in the correct material chosen for the cylinder. With the kinds of innovations that are driving the 21st century, the knowledge of how to critically examine the properties of materials for different uses helps a great deal in proper material selection, not just for the present, but also for a long time.